I'm Norman Wildberger. We have now established what null points and null lines are in universal hyperbolic geometry. These are central objects in this theory. And now that we have very explicit formulas for not just the null points and null lines, but also the lines and points determined by their joins and meets, we can go back to the first topic in this course, which was Apollonius's introduction of the idea of the polar of a point with respect to a conic, or in our case, a circle. So there's an important theorem there that I stated without any proof. And now we have enough technology to understand that theorem and give a complete and precise proof for it. This connects our current notion of duality with Apollonius's theory of polarity. So I remind you that our basic setup is that a null point is a point by definition which lies on its dual line. And we saw that every such null point, say alpha, can be expressed in this way by the use of an auxiliary proportion t to u. So for every proportion t to u, we can define this point, call it little e of t to u, given by this formula here, and that's a point on the null circle or a null point. And dually, we can discuss null lines. Those are lines whose duals lie on them. And any null line is given by this expression here with a round bracket, and correspondingly we have a function capital E of t to u that gives us a null line from a proportion t to u. And then in our last video we established two important theorems: the join of null points theorem and the meet of null lines theorem. The join of null points theorem told us what the equation of a line is through two such null points. So if we have two null points given by the proportion t1 to u1 and also by the proportion t2 to u2, then those two null points are joined by a line, and here is the formula for that line connecting those two null points. This is a kind of a bilinear analog of this quadratic expression. Let's give it a name now because we might use it a little bit. So let's call it capital F. So this is now a function that depends on two proportions: the proportion defining the first null point and the proportion defining the second null point. And there's the formula for it. And exactly in a dual way, we have a formula for the meet of two null lines. If we have two null lines, which are just lines that are tangent to our null circle, then they're going to meet somewhere. And if the proportions determining the null lines in this fashion here are again t1 to u1 and t2 to u2, then exactly the same formula, but now with closed brackets, gives us the meet of those two null lines. Now let's introduce the idea of an interior line. Let's say that a line L is interior precisely when it's of this form, when it can be written as the join of two null points. In our diagram, there's the circle. It's simply a line that crosses the circle in 2 points. It's not outside, it's sort of inside. That's why we call it an interior line. And dually, a point A is exterior precisely when it's the meet of two null lines. Pictorially, what does that mean? Well, we have our null circle. We have two tangent lines. Those two tangent lines meet at some point. That point is outside the circle in our usual geometrical picture, so we'll call it an exterior point. That's a definition of interior line and definition of exterior point in terms of null points and null lines. So here's our picture for that situation. There's our null circle. There's two null points, alpha 1 and alpha 2. So the line joining them, L, is an interior line. And null lines, for example, the tangent to the circle at alpha 1, let's call that phi 1, is a null line, and so is the tangent to the null circle at alpha 2. And those two null lines meet at that point A there, which of course is the dual to this line L. But this point here is an exterior point. So we're just observing here that if alpha is a null point, then its dual is a null line, and conversely. And so the line L equals alpha 1, alpha 2 is interior precisely when its dual, in this case A, is exterior. That interior line has a dual, that exterior point. Now let me make a warning at this point. These notions of interior and exterior are more subtle than they appear. It's not the case that every point outside here that looks like it's outside here is actually an exterior point. It's not the case that every line that looks like it's inside here is an interior line. The condition is in fact a number theoretical one. And so it may be that a line may look like it's interior, but in fact it isn't. For example, the line y equals x in the usual coordinate system, that line y equals x, does not actually meet the null circle because square root of 2 is not a rational number. So it's not included in our geometry. So this line here in fact doesn't meet the circle, and so it in fact is not an interior line, even though it certainly looks like it is. So we're not going to talk too much about interior and exterior points. Later on we'll talk more about them and we'll address this number theoretical issue. Just want to alert you to this idea that we can in fact capture the idea of an exterior point or an interior line just by the projective geometry of intersections or meets of lines, joins of points. So recall that we were quite pedantic about the difference between a triangle and a trilateral. That a triangle was a set of 3 points, which are not collinear, while a trilateral was a set of 3 lines, which were not concurrent. There's a corresponding distinction between quadrilaterals and quadrangles. So here's the definition. A quadrangle, ABCD, the bar over it, is a set of 4 points, no 3 of which are collinear. So the quadrangle ABCD is just a notation representing this set with 4 points, A, B, C, D. On the other hand, a quadrilateral, let's say capital P, Q, R, S with a bar over it, that is by definition a set of 4 lines, no 3 of which are concurrent. So this notation is just short form for this set consisting of the lines P, Q, R, and S. Alright, so we're going to use these concepts because Apollonius' notion of polarity involved 4 points on the circle, or 4 points on a general conic. So let's suppose that we have 4 null points. Alpha 1, alpha 2, alpha 3, and alpha 4. And each one of those is given by a proportion. So alpha 1 is E of T1 to U1. Alpha 2 is E of T2 to U2, and so on. Those 4 points form a quadrangle because it's obvious that no 3 of them are collinear, because it's not possible to get 3 collinear points which lie on the circle. There are 6 possible lines determined by those 4 points. We're only going to consider 2 of them at first. Let's consider L12 through alpha 1, alpha 2, and L34 through alpha 3 and alpha 4. Here are the formulas for L12 and L34 in terms of the proportions that define alpha 1, alpha 2, and alpha 3, alpha 4. This one only involves T1, U1, and T2 and U2. This one only involves T3 and U3, and T4 and U4. Now these 2 lines meet at a point. Let's call it A. That point A is going to depend on all 4 null points, or on all 4 proportions. And let's write it introducing this new function g. So we have an e function, an f function. Now we have a g function. The e function depended only on one proportion. The f function depended on two proportions. And this g function depends on all four proportions. And there's a kind of a pairing because we're taking t1u1 to t2u2. That defines our first line. Then we'll have a double bar here separating it from the other 2 points defining the second line. t3 to u3, that proportion. t4 to u4, that proportion. So how can we write down what this point actually explicitly is? We just have to use the j operation on these two expressions here. And there it is there. There are three components. First one, second one, third one. These are all proportions. So for example, the first one is this entry here times this entry here minus this entry here times this entry here. The second one, this times this minus this times this. And the third entry, this one times this one minus this one times this one. Okay, now I'm going to rewrite it, simplifying it just a little bit. It turns out that these first ones and the third ones don't really simplify. I'm just rewriting that. So there's the first one exactly rewritten, and the third one, a little bit squeezed over here, is exactly just rewriting that one there. However, the second expression, which corresponds to the kind of green geometry, it does simplify. You can cancel a few terms there, and you end up with just this relatively simple expression consisting of two terms. 2 times t1, t2, u3, u4 minus t3, t4, u1, u2. So it's a bit of a simplification, only in the middle term. That's our expression for the meet of these two interior lines determined by these two pairs of null points. So it's explicit, it's a little bit long, but not overly long. It's very amenable to calculation. And now we have complete control over the polarity of Apollonius. In any particular situation, it's probably easier just to apply the j function one step at a time to compute successive joins and meets. Let's illustrate that here with an example. 4 points, alpha 1, alpha 2, alpha 3, alpha 4 on the null circle, given explicitly in terms of these four proportions. So alpha 1 is e 1 to 1, alpha 2 is e of 0 to 1, alpha 3 is e of minus 1 to 5, and alpha 4 is e of 6 to 1. And here are the explicit homogeneous coordinates for those 4 points. So for example, alpha 4, what does it mean to be e of 6 to 1? That 6 to 1 is actually telling us the coordinate on the y-axis that we need to join with our base point minus 1, 0 to get the line intersecting the circle at our required point. So if we went up 6 in the y-axis, 6 in that direction, and looked at it from the point minus 1, 0 here, that would be exactly that line there, and that's that line that meets the circle at this point alpha 4. Alright, these 4 null points form a quadrangle, and the quadrangle has altogether 6 lines joining these 4 points. There, for example, is the join of alpha 1 with alpha 4, so we'll call it L14, and so on. And the equations of these 6 lines are just determined by the j function applied to pairs of these 4 points. You can check those values for the lines. Now the 6 lines determine 3 additional points. This happens in any quadrangle. Those 3 additional points are called the diagonal points of the quadrangle. Here they are, E, F, and G. And they're just the places where these 6 lines meet, aside from the 4 points that we already know they meet, namely on alpha 1, alpha 2, alpha 3, and alpha 4. So there are 3 other intersections or meets of those 6 lines. So for example, G, that's the meet of L12, which is right there, and L34, which is right there. It's given by the J function applied to L12 and L34. So you apply J to these two, you get this. And similarly for E, which is up here, and F, which is right there. Now that long complicated formula that I wrote down on the previous slide could also have been used to calculate any one of these. So the actual formula was actually for this one, L1, 2, 3, 4. If you plug in these for 4 proportions into that formula, you're going to get 5 to minus 2 to 3. Now a very important observation about these 3 diagonal points coming from this quadrangle of null points. Here's the very important observation. It can be stated in a number of ways, but probably the easiest way to remember it is that if you join E and F, you're getting the dual of the point G. If you join E and G, you're getting the dual of F. And if you join F and G, you're getting the dual of E. How can we check that? Well, this is really saying that, let's have a look at this one. EF, right here, we're saying that's the dual of G. That amounts to the statement that F and G are perpendicular and that E and G are perpendicular. As I remind you, perpendicularity is defined in terms of duality. Every point on this line, the dual of G, is necessarily perpendicular to it. So how do we check that F and G are perpendicular? There's F, there's G. We just evaluate 10 times 5 plus 1 times minus 2 minus 16 times 3. And that is 0, telling us these 2 points are perpendicular. Similarly, E and G are perpendicular because 7 times 5 plus 10 times minus 2 minus 5 times 3 is 0. So the fact that these 2 points are perpendicular and these 2 points are perpendicular means that these 2 points must lie on the dual of G. So E and F lie on the dual of G, so it means that the dual of G is in fact EF. This is really the statement of polarity of Apollonius. It's really telling us that the dual of G, which is this line here, can be calculated by any quadrangle of null points determined by taking 2 lines through G. So take any 2 lines through G, calculate the 4 null points, find the other 2 diagonal points, join them up, that way you get the dual of G. That was the statement of polarity. So let's record this as a theorem. The nil quadrangle diagonals theorem. If alpha 1, alpha 2, alpha 3, alpha 4 is a quadrangle of nil points, then the diagonal points E, F, and G, defined by E is alpha 1, alpha 4 times alpha 2, alpha 3. In other words, it's the meet of this line with this line. F is the meet of alpha 1, alpha 3 with alpha 2, alpha 4. And G is the meet of alpha 1, alpha 2 with alpha 3, alpha 4. These 3 points are mutually perpendicular and they are distinct. So the dual of E is in fact FG, the dual of F is indeed EG, and the dual of G is indeed EF. Just a bit of terminology here. A quadrangle of null points. I'm not going to call that a null quadrangle. I know it's tempting to do that, but I'd rather call that a nil quadrangle for reasons which I'll explain later. Okay, but let's just accept that for now. So a nil quadrangle is a quadrangle of 4 points, all of which are null. All right, the first thing to observe here, I suppose, is that we want to show that these 3 diagonal points are in fact distinct. So suppose otherwise, suppose that E equals F, that these 2 points are actually the same. Well, then that common point E lies on alpha 1, alpha 4, and also on alpha 1, alpha 3. But these 3 points, alpha 1, alpha 3, and alpha 4, are not collinear because there are 3 null points. 3 null points can never be collinear. So, alpha 1, alpha 4, and alpha 1, alpha 3, E lies on both of those lines. So, and those are not collinear, so it means that E and F must actually be the common intersection here, which is alpha 1. But then by symmetry, correspondingly, E and F also have to be equal to, say, alpha 2. So we get alpha 1 equals alpha 2, which is impossible. So the 3 points are distinct. Why are they mutually perpendicular? Once we know that they're mutually perpendicular, then, as I observed in the previous slide, this will follow pretty well immediately, because we know that the dual of E is obtained by taking 2 points which are perpendicular to it and taking their join. So why are these 3 points mutually perpendicular? That is a calculation which we are now going to do. So how do we check whether 2 points are perpendicular? Well, we have to multiply the 2 first coordinates, we have to multiply the 2 second coordinates, we have to multiply the 2 third coordinates together. We have to take the product of the first plus the product of the second minus the products of the third, and hopefully that's going to be 0. Do we know the coordinates of F and G? Yes, we do. That's exactly that G function that we were talking about before, not to be confused with this point G. All right, so F, for example, is the meet of alpha 1, alpha 3 with alpha 2, alpha 4. Here's the first coordinate of F, here's the second coordinate of F, and here's the third coordinate of F. Here is the first coordinate of G, here is the second coordinate of G, and here is the third coordinate of G. So we have to multiply the first coordinate of F times the first coordinate of G. Then we have to add the second coordinate of F times the second coordinate of G. And then we have to subtract the third coordinate of F times the third coordinate of G. And we have to do some work. We have to expand that thing out. And when we do, collect all the terms, everything cancels, and we get 0. And that's why Apollonius's polarity result works. This is a proof of it, a purely computational proof that essentially involved no thinking. We didn't do anything clever, we just computed, but you have to put some work in to expand this out and to simplify it. Okay, by symmetry, once we've proven F is perpendicular to G, well, it's the same story. G is also perpendicular to E, and E is perpendicular to F. And now what I said before, since G and F are distinct and both perpendicular to E, the dual of E is in fact FG, and similarly the dual of F is EG, and the dual of G is EF. So this establishes that our notion of duality, which ultimately was very simple-minded, right? Our notion of duality was just we're going to change round brackets to square brackets. That's all. But now this establishes that that simple-minded notion of duality is in fact really the same as the idea of polarity going back to Apollonius. In other words, if you want to compute the dual of A geometrically, what you can do is you can take any 2 interior lines through A. In other words, lines that pass through A and also through the null circle. Say those black ones. Then you get 4 null points forming a nil quadrangle. You can take the diagonals of that nil quadrangle, giving you 2 more points. And then you can join those 2 points up and you're going to get the dual of A. And now we know that what you get does not depend on these 2 lines that we started with. You can move these lines around. As long as they go through A, that quadrangle of null points that you get will give you the same dual line once you join its 2 diagonals. Okay, and so since our homogeneous coordinates can be transformed into affine coordinates by dividing by c if c is not 0, and since we know that the line A to B to C really has equation ax plus by equals c, we can deduce that the dual or the polar of rs, say this thing here, is indeed the line rx plus sy equals 1. Because duality and polarity just amount to changing round brackets to square brackets and vice versa. Next time we are going to introduce symmetries into our hyperbolic geometry so far. The basic symmetries, the most fundamental symmetries in geometry, are typically reflections. So we're going to talk about reflections in points and reflections in lines next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.